Okay, we are now in chapter 6. All right, so chapter 6 is about the reciprocal lattice. I believe that you have heard about this term for many times in chapter 5 and in maybe chapter 1 if I'm not mistaken. So now this chapter will introduce you the concept of the reciprocal lattice. We will learn how useful the reciprocal lattice is in the study of the crystal structure in the diffraction theory. Okay, of course, this reciprocal lattice is not only useful in diffraction theory, but it's also very important in the band structure. Okay, for the band structure, like energy gap, covalent band, valence band, these are all constructed under the reciprocal lattice, not the real lattice. In the diffraction experiment, for the example X-ray scattering, the result obtained, the reflection pattern, give direct information on the reciprocal lattice rather than the real lattice that we studied earlier. So naturally, if we know the reciprocal lattice is a trivial method to work out the real lattice. So in this chapter, I will tell you what is the relationship between real and reciprocal lattice and what is the equation to convert the real to the reciprocal lattice or from reciprocal lattice to real lattice. Okay, so this is the picture of the diffraction pattern. So from this reflection pattern, we can get the information of the reciprocal lattice instead of the real lattice. Okay. So for example, this is the diffraction pattern that we collect directly through the camera, and then we digitalize it. We digitalize it into this form. Okay, so for the example, this form is say that h equal to bar 1, so h equal to bar 1, k down from this spot, k down positive, k up negative. So to the right positive L, to the left negative L. Okay, so we can see that, okay, let's say for this spot, h equal to -1, always -1, and then L 1 2 1 2. So L equal to +2, and then K equal to -1, right? Because in this direction negative K, so this is -1. So K equal to -1. So the HKL equal to -1, 2 for this spot. Okay, so this HKL basically is just a reciprocal lattice axis. Okay, in the real lattice we have S, Y, Z, right? But then in the reciprocal lattice we have HKL. Remember in the third chapter we studied the Miller index. We have A, B, C, then HKL equal to 1 over A, 1 over B, 1 over C. Remember that? So HKL basically is the position of the reciprocal lattice. Therefore, the diffraction pattern gives us the direct information on the reciprocal lattice. So later on, we need to process it and then convert it back to the real lattice. So there are two types of lattices in the crystal structure. So we have crystal lattice, Ravel lattice, or real lattice is the first category, and the second category is the reciprocal lattice. For the real lattice, it can be investigated using the optical or electronic microscope, okay, because we can just look at it directly because it's real. But then for the reciprocal lattice, we have to use the diffraction technique, okay, diffraction technique that we have discussed in last chapter. So for the real lattice, the translational vector have distance as dimension, so we normally use t. And then for the reciprocal lattice, the translational vector have inverse of distance as dimension. Normally we use g. Okay, and then the coordinate we use s, y, z. Coordinate we use h, k, l. And the relationship between reciprocal and the translational, for the simplest way, g equal to 2 pi over t, or g equal to 1 over t. Okay. So for the crystal lattice is in the real space, and then for the reciprocal lattice is associated Fourier synthesis space. Okay, so Fourier space, that's the reason why we need to use the Fourier synthesis to convert the reciprocal lattice to the real lattice. Okay, reciprocal. Reciprocal just means songsangan, inverse it. So in fact, you have heard about this term before in the mathematics. We have reciprocal of sine, reciprocal of cos, reciprocal of tangent, we got cotangent, right? So cotangent, reciprocal, you will get tangent. So this is basically just real and reciprocal. So the diffraction pattern and reciprocal lattice, the scattering of radiation and interference between scattered photons produce the resulting pattern we call the diffraction pattern. Note that from the Bragg law, there's a reciprocal relationship between the distance between the row of scattering standard d and the scattering angle theta. Why it says so? 2d sine theta equal to n lambda. 2d equal to n lambda over sine theta. So this d and sine theta have the reciprocal relationship. D proportional to 1 over sine theta. Then this is a reciprocal relationship. Therefore, there's a reciprocal relationship between the unit cell of the crystal and the lattice pattern of the diffraction spot. Okay, so just now I said that sine theta is proportional to 1 over d, right? So this d is the real lattice. So this is a plane of the atom, and this is another plane of the atom. So the distance between these two planes will be d. How about sine theta? Sine theta means that the diffraction, okay, different theta will give you different diffraction spot. Can you imagine that? Oh, it's not here. Okay, so I have the crystal. I use the X-ray to hit the crystal, then it diffract. Right, diffract. So this spot is here, this spot is here, this spot is here. So you get 1, 2, 3, 4, 4 spots, and all the position of this 4th spot depends on the theta. Okay, so therefore here it says that the theta is related to the reciprocal lattice because the refraction spot is related to reciprocal lattice, whereas the d is related to the real lattice. Therefore, from the Bragg law, we have sine theta proportional to 1 over d. Sine theta, the reciprocal lattice, and the real lattice, this is the relationship. Just like g proportional to 1 over t, reciprocal, real. So now we consider normal to all possible direct lattice, like this one.